good morning, folks. My name is Omer. This is Ricardo.
Hi, everyone.
We're going to talk a bit about hardware and software and IoT and all the niceties that come with it. But this is mostly almost a story of how we worked on this project for over a year now, and we built a little software, hardware IoT platform, using the beam, of course. So my name is Omer, again. I'm a hardware and manufacturing consultant. I used to work at ESL, and I worked on the Erlang embedded project where we explored, this is 10 years ago, just about, when we explored ultimately how we could use the niceties of the language on Linux class devices.
And my name is Ricardo Lanziano. I'm a software engineer at Erlang Solutions, America's office. I also have a background in firmware development, and this is how things get excited.
Yeah, so the interesting thing is that we've been working on this project for over a year now, and George, who's not on the stage with us, is also part of the team. And yesterday was the first time we were in the same room. So over a year of talking, and thank you for facilitating this, organizers and ESL staff.
Yeah, thank you very much.
So what we're going to talk about today is very briefly IoT and the trends that we're seeing. And then we're going to talk about how this project started and how it evolved, more importantly. Again, this is meant to be more of a story of an R&D project. And then we will introduce you to what we're now calling the ESL Reference IoT Reference Platform and a custom hardware and software solution that we built. And
yeah, we're also going to talk a little bit about why we chose Erlang and all the tooling that comes around, the insights and the challenges that we found during this process, how we overcome them, what is still missing, and we're going to close up with the future explorations of what the reference platform would look like and the ideas that we have for the future.
This is 10 years ago in this very room, and we're still talking about Internet of Things. So, obviously a lot has changed, but this is to say that embedded and Erlang are not necessarily, new concepts. They're not new pairings. In fact, in a few slides, we'll talk about how we see the Erlang as the original IoT, embedded platform. But really, it's going to be fun. So really, in the IoT world, what even is IoT? IoT is anything and everything, much like how cloud computing means anything and everything these days. But the trends, hypes, and realities is that we're currently seeing much faster, a lot better processors. Heterogeneity is a thing. Machine learning accelerators being part of silicon is very much a thing. So it's a great time to be speccing embedded devices, and they run very fast, and they run a lot of things as well, to the point where you can just run Linux and anything that runs on Linux without needing to worry about even cost or complexity. The only time this gets a bit complicated is when you have certain low power and super cost efficient solution requirements. But more importantly, for the context of this presentation, what kind of are we, or what type of IoT are we talking about here? So really, we're focusing on building interfaces across a different set of, or different classes of devices, and one of the keywords being multiprotocol and multi-link, and effectively putting together a development platform that allows us to experiment and build these types of systems quickly using some very nice frameworks and tools.
Yeah.
And really the key point is that no matter what the latest trends are, really we see IoT as primarily involved in interfacing things. Things is a good word. It's a very generic word, but things could be battery, coin cell, battery-powered little sensor devices, all the way to other types of gateways that have a redundancy kind of structure built around them.
And what we mean by that, connecting devices and interconnection, it's pretty much this picture that we have here. This is a generalized topology of multiple scenarios that we have been seeing recurrently in IoT deployments. The pattern that we have observed is that you have a gateway that is able to aggregate data from different or plethora of devices that are connected from whatever medium, and it can be expanded to a new frontiers to then take that data out and pre-process it in order to either store it in some cloud-based operator or in-house premise installation. So this is basically the conceptualization that we have been working on.
So the way that we started this project out was, it really was trying to answer or figure out a requirement set out by a customer. And broadly speaking, it was, how can we interface a legacy device that has a wired RS-232 serial interface to our in-house backend systems, on-prem backend systems. But of course, Ricardo and I have worked on IoT devices and IoT gateways and these classes of devices in the past, and we kind of turned this into a bit of an R&D project, and it was a development platform by developers for developers kind of an approach in which we tried to capture through different iterations and explorations, we tried to capture quite a few of the common, interfaces, radios, stuff that we would need to build these different scenarios and use cases. And really, this, as I've mentioned before, this turned into a bit of an R&D project where we built, a generic enough hardware-software combo platform that allows us to quickly iterate over these things.
Yeah, and as Omer is mentioning, we organically grow the platform according to our needs and our understanding, and also based on previous experience. And we also have a wish list of stuff that we wanted to see based on everything that we have been working before previously. So this started to grow organically up to the point that we were comfortable enough to start rapidly prototyping new alternatives. And this allowed us to mature the platform in a way that we now consider it the reference platform that allows us to provide proof of concepts and MVP very quickly in the IoT landscape.
So what is the ESL IoT reference platform? And I'm just going to read this slide. It is a combination of co-developed, cohesive set of custom hardware and software components. And the key word here is that it's, we worked on this together to the point where Ricardo is responsible for the color of the LEDs on the board kind of detail. So, really every aspect of the hardware decisions were, done and implemented with ensuring that the software side, Ricardo was happy about it.
Yeah, and vice versa.
So, it's really designed to work with a set of, wired and wireless different links, both wired and wireless and multi-protocols and devices that actually can communicate over these types of different protocols.
Yes, this is currently on the works, but we are using this vessel as an exploration in different IoT scenarios, different solutions, and we also use it for research and development of what we think the whole platform should look like in terms of provisioning, interoperability with other protocols, and what's not. So, let me start up talking a little bit about the device abstraction layer and what do we mean by that, because this was one of the things that we really wanted to tackle from scratch. We base ourselves in a lot of work that has been done previously in those topics, mostly when it comes to machine-to-machine interoperability. The reason that we started to do this from scratch is because we not only wanted to have fun, but to solidify previous experience into something that is very cohesive and proper tailored to when it comes to OTP applications. That's basically the excuse that we have. And for that, we base ourselves loosely in two different kind of frameworks and working group recommendations. There's the OSGI working group that specifies a set of rule sets and best practices when it comes to develop Java application at the enterprise level for tackling these IoT problem domains. And there's also the Apache Camel architecture reference. This is something that I got from Fred Dushin from the Atom VM guys. Thank you very much. And it allows us to build a data ingestion pipeline in a way that we can tweak it on the fly when, at runtime. And basically, what we distill from these two different projects is their ability for dynamic reconfiguration on the fly, their modularity, and the different abstractions when it comes to multi-links and protocols. That's basically it. And we built this on top of Ecto, PG, Broadway, and OTP. That's our secret sauce. And what we mean by that is we distill some of the core concepts that the OSG working group and Apache Camel provides and accommodate those to our understanding. This is devices, function, the different data that they generate, how we can properly filter and provide transformations of those data, and the different DSL that we implemented for being able to dispatch those events easily to endpoints at the end of the staging. There are also another alternative that we have been keeping track of in terms of concepts and inspiration from. To name a few, I'm not sure if you guys are familiar with Home Assistant. If you are, well, this is basically what we're trying to achieve in a much smaller scale, of course, but the overall idea is for us to be able to plug devices and take out the different functions that they provide, be it temperature or whatever reading that they provide, and organize them cohesively in a single dashboard for us to either transform those data or perform other operations later on. When it comes to the data ingestion pipeline, I'm going to keep this very brief, but basically what we have from Apache Camel ideas, it's the different stages and different processes and interfacing that needs to be taken into consideration in order for us to flip and switch filtering, routing, and transformation routines on the fly. This is basically the flow of the whole pipeline. You have devices that can be connected to any kind of medium. You then ingest those data, provide transformations to be then delivered those. When the data is actually filtered and transformed, then you dispatch it to endpoints. And when endpoints, we mean the subscribers of those data. It doesn't mean actually an actual endpoint, HTTP, but just the final result. And when it comes to the data model, the way that we organize this, based also again on OSGI, it's a way for us to abstract what the device and the functions that they provide, how they interact, and how they can be switched off and on the fly. Roughly speaking, we have a set of devices that are going to provide certain functions to the system. It could be temperature readings, it could be actuators, it could be whatever. And those functions will emit data once they're finished their pipeline transformation. The data is then emitted by certain types of events that will also contain some metadata that is attached to them. So we can start applying those transformations on the fly within the data ingestion pipeline. And the end result of this is events being emitted and subscribers being able to ingest those events once they finish the whole stage of the pipeline.
So let's talk a bit about hardware. Well, I mentioned that this is an R&D project, but we just didn't put together a few Raspberry Pis and called it a day. So we built custom hardware to satisfy the requirements that we set out for ourselves. And tangible physical hardware is always good, but we're not doing live demos on the stage. But after Frank's talk, we'll be setting up and come and play with our hardware and stuff. We'll have a demo and we'll talk about that in a second.
Please join.
But Gateway version 1 is a nice little metal box that also has some wall mounting options. It has a few different wired interfaces. Again, we tried to pick a few common interfaces that we could build proof of concepts really quickly with. So on this particular implementation, we have RS-232, RS-485, CAN, and MBus. And we also have a very nice little tiny OLED display. And yeah, it's built around a common single board computer that is very well supported by nerves. And yeah, there's also internal expansion by way of USB and a few other GPIO pins exposed, so we can actually build more stuff inside this if we need to. And I mentioned that this is really designed by developers for developers, so there's a USB console. You can just power and get data, a console out of a single USB-C cable, because terrible development boards we've had enough of those. And we also have a little demonstrator device. This is a very, very simple, based around a common wireless microcontroller device. You might not be able to see the screen, but actually Ricardo put together a nice workshop running on Atom VM. So you can, if you come and join us later, you get to write some Erlang code and look at some Erlang code running on this device, thanks to Atom VM.
Yeah, thanks.
And this is a really, we call it the end device demonstrator. It has a temperature and humidity sensor, some LEDs, some buttons, and it also allows you to add more sensors if you want to. It's battery powered, so really this allows us to quickly experiment with end devices. Now, a special class of end device is our bridge device that lost its top on the way here. But the idea is that this is a special class of end device that allows us to link effectively or bridge legacy devices that may not necessarily be able to talk to the gateway directly, talk to the gateway directly by acting as the bridge. So, you know, similar to the set of wired interfaces we have on the gateway, this has RS-232, 485, and CAN bus. But more importantly, they're galvanically isolated so that, you know, there's a electrical barrier between what we're doing and what the legacy device is doing. And this is really meant to be a little simple, cost-effective device that can be deployed to link, you know, slightly older devices that may not necessarily speak Wi-Fi or wireless protocols that we are supporting.
Yeah. And when it comes to the communication overview, this is a general glimpse of what we have right now as for today, and we're also showcasing this in the demo. We are currently using Wi-Fi, the stock Wi-Fi infrastructure. This is easier for us when it comes to building and prototyping, also when it comes to the workshop itself, but it also allows for rapid prototyping. We are currently also working in different links and mediums in order to make them pluggable and switchable on the fly. There's also communication protocol abstraction, so we're also able to switch between different protocols, and there's serialization on the fly at the device level and at the function level as well. There's a couple of things that are currently missing when it comes to provisioning and firmware upgrades, and this is mostly because the gateway itself has an integrated microcontroller that we want to also upgrade and roll back when we do the NERVs operation. And this is something that it's taken a bit, but we will get there eventually.
Yeah. Actually, on that topic, one detail is that we talked about the wired interfaces, but as you can probably guess, there's also 3 radios in this as well. Different class of radios that supports different protocols and so on. So with a further expansion available for even more radios. So it's a development board, but that allows us to really explore all the different wired and wireless protocols.
Yeah, and this is also the idea, because if we feel that we need to prototype or take advantage of some other medium, we can easily do that. We can easily modify the gateway and come up with software requirements in order to just prototype and validate the ideas and the concepts before landing somewhere else. So that's basically what we have. And the future goals when it comes to the gateway and the radio in particular is that we're exploring mesh connections. We're exploring P2P connections when it comes to, right now when it comes to Wi-Fi, but we're also exploring other communication links, especially sub-gigahertz protocols. We believe that there's some advantage to be taken there. There's some new protocols that are somewhat more resilient when it comes to dropping connections than Wi-Fi. So this is something that we are keeping tabs on. I believe that that's the future, right?
Yep.
And when it comes to protocol translation and function discovery, this is the last part of the whole pipeline ingestion, and the way that we handle the events is that we also take advantage of different projects that we have worked before when it comes to abstracting drivers and how we can operate on different protocol formats. So this is already taken care of, this is in place. What we do is that we have a set of driver devices and also adapters that can be switched and toggled off and on that provides easier auto-discovery of the functions that the device provides. And this is also a way for us to register those functions into the system so other people can be aware of what's available and just ingest the data once they subscribe. So this is mostly what we have. There's still some rough edges at the end because we need to further iron out some details, but it's there. And this is all based on function event handling. This is the final result of the pipeline, and from there on, it's just about integrating with other systems and other services.
So we use NERVs, but we're not going to talk about NERVs because Frank has a talk right after ours, which you shouldn't miss. But hands up if you've used nerves before or heard. Amazing.
Oh yeah,
great. Nerves is great. Thank you, Frank.
Thank you,
team.
Frank, very much.
But what we're going to talk about is how we use nerves and the kind of customizations we had to get our custom hardware up and running. So, I mean, this is kind of an obvious slide, but take it away.
Yeah, this is very obvious. It's no strange for us that nerves has this amazing, welcoming, and experienced community that we have been leveraging in all the possible ways that we can. Thank you very much, Frank and the team, for making this happen. We also picked nerves because we have built-root familiarity. We have been working in different projects in the IoT landscape before, so this was something that is very great for us, and it also allows for a more streamlined developer experience. This is something that was not possible a couple of years back, a decade ago, but nevertheless, the landscape is changing, and I don't think you can go wrong with picking nerves when it comes to developing solutions for IoT. And of course, Erlang OTP, we use it very heavily. Everything that it provides, we're standing on the shoulder of giants. And what exactly did we do with nerves? Well, there's not much to it because it's pretty satisfying experience, but we did have to come up with the custom system image because we have some hardware particularities that we need to take into consideration when it comes to wiring the different address and the U-boot overlays. We also needed to add a couple of custom driver for the Wi-Fi controller that we have. Some extra CAN and modules, kernel modules needed to be in place for us to use it. So there's a couple of things that we added there. And special care when it comes to the ESP SDK integration. This is something that we really need to have within our image because it will allow us to start tweaking and prototyping how rollbacks and upgrades is going to look like when it comes to the microcontroller itself.
And Python to support.
Oh, of course, Python. This is all the tooling is written in Python. And
so, as Ricardo mentioned, life was very different, a decade ago, and I think the cat faces really kind of explain the situation. If you would get a tarball of questionable provenance, and good luck compiling it. Security updates, forget about it. But really, OpenWRT kind of was the best option.
Was it only option?
Well, yeah, kind of. Definitely, actually. Yeah. And then, we're much happier now, much like that beautiful orange cat. So, yeah.
Yeah, and there's another distinction that we need to make here is that there's actually two sides of the stories. We have, there's a different categorization when it comes to device classes at the IoT world. Right now we have two of them working on the same gateway. We have the system on chip, which is running Linux on nerves, and we also have a microcontroller, which is running the Express IDF SDK, which is written in C. So we basically have two worlds, two languages in the same platform. There's C and the specific vendor SDKs that we need to use, and everything else is in Erlang and Elixir when it comes to nerves. But there's also a special mention that nowadays it's easier to run Erlang-based code in microcontrollers using Atom VM. So it's possible nowadays to come up with some Elixir, Erlang, and LFE examples for in this little device right here. Thank you for this. The Atom VM guys did an excellent job of providing a new release for us to play with this. So thank you very much.
So, I mean, I kind of alluded to the fact that we consider Erlang to be, the original embedded platform. That's obviously tongue-in-cheek, but really, if you think about it, it was designed to run on embedded devices, telephony switches, ultimately by the very definition of what an embedded system is. So, really, this is not new. We're just, once again, standing on the shoulders of giants. And there are a few facilities that Erlang provides that are super, super useful. So as a summary of what we're using.
It's obvious that OTP shines in everything that we try to make out of this gateway. But particular mention to binary pattern matching, fault tolerance, and predictability. These are key characteristics that we find very appealing when it comes to developing and shipping IoT products in the wild. We already know the story about concurrency, we already know the story about distribution, but right now when it comes to the gateway and our experience, binary pattern matching and predictability of operation has been golden, mostly because those devices are expected to run in a lower power, and they're not fast enough, like our laptops. So we really need to have predictability when it comes to operations, and fault tolerance, it's an obvious choice. So, or insights when it comes to what we learn on this journey when developing system for the gateway is that interoperability is crucial. We really need to think about how multiple protocols can interoperate with each other and how can we make sense out of these heterogeneous environments. I think that's key here. Reliability at scale, this is something that Erlang and OTP provides. I shouldn't spend much about this, everyone knows about this. Efficiency on development, this is something that I really need to stress out because what Elixir and Erlang provides, what Nerves provides, it's a platform for developers that are not used to embedded devices to come and work on them without any fear and without any problem. And this was not possible a couple of years ago. So we're very grateful that this exists because it allows people to jump into new problem domains without having that much friction when it comes to going into embedded world because it takes a toll. So I believe that this is something that needs to be very highlighted.
Highlighted, definitely, yeah. And again, the state of affairs in generic embedded platforms and frameworks, etc., is that, yeah, you get a running Linux instance, but the fact that Nerves boots into the runtime and you're not really, you have all the tools and niceties that comes with that is something that is actually quite impressive.
Yeah, and you don't need to change your development workflow when it comes to make things work. So I really love that. Yeah. Obviously, OTP, there is development. There's a lot of code that we reuse on OTP, and it's highlighted in the gateway. Please talk to us when Frank's presentation is done, because we're going to showcase everything that we have been talking about. Where is the booth? Right next to the Erlang Solutions
Commandant's room? Downstairs. This last heading is something we've debated for a long time and couldn't really figure out the right terminology. So for lack of a better word, we're calling it the edge computing capabilities. So what we mean by this is that the new model in which we look at gateway devices as being, the edge devices, edge nodes, etc. Really the model is that we focus on making the end devices and the bridges work as well as they could by allowing them to communicate with the gateway directly. In some cases, this is absolutely necessary. In cases where end devices or bridges cannot actually reach out to the wider internet, you do need a gateway. But even if they were based on Wi-Fi, actually allowing the gateway to be the supervisor and manage all the, what you would expect, facilities like firmware update or supervision and monitoring and logging, etc. That's kind of what we're trying to talk about there.
Yeah, we want to push it as much as we can to run tasks on the bridges themselves, when it makes sense.
And really, I think the emphasis is that, I'm very proud of this slide. So really, we designed this with hardware and software really, in conjunction, all together, the hardware and software decisions taken, in beautiful harmony. Anyway. So, but it didn't come without its challenges as well.
Yeah, no, it was a little bit of, it had pains. One of the main points that we are trying to address here is the integration, as I mentioned, the integration between the system on chip and the microcontroller when it comes to provisioning. Rollbacks, upgrades, validate that everything is working properly. That's something that we need to stress out. It's a work in progress. There's also the testing suite because, trying to design for multiple protocols, there's extra testing that needs to be taken in place, and we're currently missing that. We're working towards that. It's a big challenge at the moment, but we'll get there. Provisioning, authentication, and security, it's also something that we have been discussing ourselves. We had our own custom ad hoc provisioning mechanism, but we really want to open up the possibility to talk to third-party solutions, cloud services, in order to take advantage of their offerings. So this is something that needs to it's a very big challenge, to be honest. But
yeah, and also generalizations are just hard, right? So especially when building hardware, you're committing to part numbers and wires and connectors and whatnot. So again, we try to capture the common set of things that we have used in the past and we know we will use going forward. But yeah, this has been actually quite just from a specification point of view. And the last point is actually quite an interesting one because, we have several radio modules on there and interoperability and coexistence when you have multiple radios is quite problematic. Yeah. And we're thinking of adding more radios, so there's quite a big challenge there. Yeah. But again, it's very unlikely that in a production deployment we will have 3 radio modules. It's not just a coexistence nightmare, it's also a compliance nightmare as well. So again, this is a development platform and we have a lot of fun.
Yeah, well, that's a very valid point.
So yeah, there's more stuff to explore. There's never enough time to explore all the things we want to explore.
Yeah, this is what the future looks like when it comes to the gateway itself. We're looking at from the hardware side of things.
Yeah, so we can always have a faster processor. Yeah. We can always have more heterogeneity. We can always have an accelerator that we can throw some ML workloads at. But again, the focus for version 1 was interfacing and making sure that we, provided a nice kind of platform for specifically interfacing applications. But version 2 could definitely have a different SBC, different SOM, different processor that allows us to do more things with it as well. On the connectivity side of things, we talked about sub-gigahertz radios. Sub-gigahertz radios are great because 2.4 gigahertz is a very crowded place to be. And just the penetration of just the physics of it allows sub-gigahertz radios to cover a wider area. And peer-to-peer and mesh networking, we already have hardware support for this. This is more of a software exploration. We actually have 2 radios that can support different kinds of mesh networking scenarios. And on the software side?
Yeah, on the software side, we've also been keen on trying KOS, the Kryten Secure Operating System. This is something that we have been keeping tabs on because we think it's a very interesting project and the future of it looks very bright. We are also in talks when it comes to multi-gateway redundant deployments, and this is having to deploy multiple gateways and being able to share load with each other in case for redundancy purposes, I must not.
So we actually have a fair amount of time, so we can talk in detail about the kind of conclusions that we have come to.
Yeah, that's right.
Yeah, so we started really with a single requirement that was fairly well defined, and but again, we decided to take it a bit further, and really, we have developed enough IoT gateway prototypes, etc., that we didn't want to repeat what we did once again, so we turned it into more of a kind of an R&D focused project, really. And then the end result is the version 1. It's quite important to stress that this is a version 1 of our reference IoT implementation. Yeah, we invite you to come and have a chat with us. We're very keen to hear thoughts and run some demos. We might even provide you with some candies. With our custom-built candy dispenser that runs over RS-232.
Yeah, that's nice. We also want to stress the fact that we took this opportunity to understand from our past experience how the whole device orchestration and framework side of things should look like. And we also throw a couple of wish lists at it, and it started to evolve organically. And this is the end result, but by no means this is the actual end product. This is just our research and development platform that we're going to use to further tailor out further requirements in different IoT landscape and scenarios.
So it's important to, and we touched on this earlier, but generalizations are hard, as we all know. So early feedback from actual partners really helped us shape the way we built solutions, and we're keen to have more of those conversations. And yeah, definitely, let's chat.
Yeah, and we had a lot of fun with nerves. Can't stress that enough.
Yeah, so I think the next point is very obvious. We have manufactured our own platform. Small-scale hardware manufacturing is always fun. We can definitely talk for hours. If anyone's interested after this, come and find me. And yeah, I guess this kind of concludes what we are talking about. We also have some boards that we can probably hand out. So if you're interested in contributing to Atom VM, or if you're interested in building, little sensor devices running Erlang or Elixir or LFE, Let's hack some LFE. Let's come and find us.
Yeah, let's do it. We're just right next to the corner.
Absolutely. So yeah, that kind of concludes our presentation. Thank you for listening, everybody. And if you have any questions, I think we have a few minutes to chat.
Thank you very much.
Thank you so much. If you are online and have questions, please throw them up on the Whova app. I'll be checking that and I'll read them out. And if anybody has any questions in the room, we do have a few minutes before we need to move on. Yep, Frank.
Go easy on us, Frank.
Yeah.
Oh, first of all, I was going to say the pictures of your boards look beautiful. So
thank you.
Great job on those. And I look forward to seeing them for real a little bit later. But I was wondering if you could talk about the communication interface between the NERS part and the AtomVM part and what that looked like and like what your thoughts were on what protocols to go over that.
Communications between the NERS app and?
The NERS app, so how you could call functions, invoke actions on the ESP32 in AtomVM.
So right now, like starting with the hardware picture, right? So right now we have a UART and a few extra pins that we could implement a higher level protocol in. The current implementation is a fairly straightforward passing messages over UART. So it's a nascent exploration into how the data model fully ties in with the external microcontroller running and into the application. And that's something Ricardo has been exploring.
Yeah, that's one way of communicating. The other way that we have demonstrated right now is TCP communications. So we're connecting via Wi-Fi, TCP, we're serializing to Erlang terms because we want to showcase also the switchable nature of the protocol serialization. But right now, I believe that's some said. We have two means of controlling it. One is UART inside the gateway itself, and when it comes to bridges and external devices, we're just demoing with TCP Erlang terms.
Yeah. There's definitely more work that needs to be done to tie in the full, beautiful data model abstraction of functions and function events and how they get translated. Not just from the ESP side of things, but we also have a 802.15.4 radio in there as well. So Thread and Zigbee are also things that we can potentially explore.
Yeah, and there's also bidirectional communication.
All right, we are running out of time for questions. If we have one more, if it's a quick question, we can do it. Yeah, come on. Isaac.
Yeah, so the reference board that you have a picture of there, what sort of extra things, extra sensors and stuff are on there besides just the temperature and the humidity?
So on this photo, we have an SCD40 carbon dioxide temperature humidity sensor. But if you notice, there's some extra holes in there. So this can accommodate the common breakout boards from the prototype suppliers that you're probably familiar with. It's just a matter of finding the right holes to mount them. And the interface we use is like a standardized I2C interface. Just Quick or Stemma QT is the name of it. And yeah, you know where to go for finding sensor boards, I guess. Sorry? Yeah, I2C. So the little cable, I should have picked a better cable. It's black, so it blends in with the board. But yeah, this is an I2C interface between the actual board and the sensor module. So cool.
All right, Omer and Ricardo, thank you very much. Got to see their demo.